everybody. This is Barney Fife, and here's board problem 40. To conduct a survey of holiday shopping patterns, a researcher opens a telephone book to a random page, closes her eyes, puts her fingers down on the page, and then reads off the next 100 names, which are true. The survey incorporates chance. I suppose a little bit. The procedure results in an SRS. I don't think so, because a simple random sample means if you're going to pick 100 names, each of the 100 names have to have an equal chance. And since we're talking about shoppers here, and they're just shoppers, telephone books, and in a telephone book you can have lots of people with the same last name, and they would have maybe similar shopping patterns. So I don't think it's an SRS, you guys. And let's see, the procedure could easily result in selection bias. Well, yeah, if there's lots of bullocks in there, then it certainly could, you guys, or whatever. Okay, so looks like choice B on that one, all right? And there's the explanation that your wonderful teacher put for you guys right there. You can pause whenever you want, and I'm not going to pause. Here we go. Okay, this is section 8.1, the binomial distribution. This is an easy lesson, you guys should go fast. In a binomial setting, each observation falls into one of two categories, either success or failure, on or off, light or dark, left or right, heads or tails, one of two categories, okay? And then there's a fixed number of observations, so it doesn't go on to infinity, you guys, so you stop at a certain number. And the n observations are all independent of each other, like flipping a coin. Those are independent. The first flip is independent from the second flip, from the third flip, and so on. And the probability is the same for each observation. Okay, if the data gives a binomial setting, which is those conditions we just discussed, then the random variable x is the number of successes is called a binomial random variable. And the probability distribution of x is called the binomial distribution. Okay, just some names, you guys. And we write it like this, with a b, which means binomial, so the n means normal. This small n means the number of things for, so if we see a b in front, we're talking about a binomial distribution. Here's the number of observations we're doing, and here's the probability for each one of those. They're the same. Okay, n is the number of observations, and p is the probability. Okay, and the big B stands for binomial. Okay, so pay attention to the binomial settings, because not all of them are binomial settings. I'll show you an example. Here's the blood types. Example 8.1 on page 440. Blood types is inherited. Both parents can carry genes for the O's, type O's and type A bloods, and each child has a probability of 0.25 of getting an O gene, two O genes, and so having blood types, having the O blood types. Okay, different children inherit, sorry, my bar's in the way, I'm getting a little confused there. Different children inherit independently of each other. Okay, so there they are, independent, need that right there. And the number of O blood types among 5 children, so there's our N, our 5 children of these parents, is the count X of successes in 5 independent observations, and each one has the probability, the same probability of 0.25. So it does fall into a binomial distribution. So we can write it like this, you guys. B, there's the number of people that we're doing, and each one has 0.25. So just that one could be a binomial because it satisfies all the categories. Okay, so dealing cards. Example 8.2 on page 440. Okay, deal 10 cards from a shuffled deck and count the number of X red cards. Okay, there are 10 observations, and each gives either a red or a black card, and then a success is a red card. But these observations are not independent of each other, I hope you guys can see, because the first card is black, the second card is more likely to be red, and so on. If the first card's red, then the second card is more likely to be not red. So the cards are not independent of each other because you're not replacing them, so this does not have a binomial distribution. Okay? So inspecting light switches. An engineer chooses an SRS of 10 switches from a shipment of 10,000 switches. And suppose that the unknown to the engineer, 10% of the switches in the shipment are bad. All right, so the engineer counts the number X of bad switches, so there's our number, in the sample. Okay, so this one is not quite a binomial setting, because when you remove one card, just like removing the one card in the prior example, if you remove one switch, it takes the proportion of the bad switches remaining in the shipment. So there's 9,099 left in the shipment right there. So the state of the second switch chooses is not independent of the first. But in this case, you guys, by removing one switch from a shipment of 10,000, changes the makeup of the remaining 9,999 switches. It changes it very little. So in practice, this distribution is very close to a binomial distribution. So when you're talking about big numbers like this and you're only taking one away where it doesn't change it that much, you can go ahead and set it up as a binomial distribution. And you'll see that in the next lesson. We use this example, okay? All right. In fact, my friend Gomer Pyle is going to help you with that lesson. Okay, let's see. Aircraft engine reliability. So this is example 8.4 on page 441. Engineers define reliability as the probability that an item will perform its function under specific conditions for a specific period of time. If an aircraft engine turbine has a probability of 0.999 of performing properly for an hour of flight, the number of turbines in a fleet of 350 engines, there's my N, and my P is this guy right here, okay, 350 engines that fly for an hour without failure has the binomial distribution B 350, there's a comma hiding back there, 0.999, so it's a binomial distribution, okay, because the binomial distribution is obtained by assuming, and it seems reasonable, that the turbine engines fail independent of each other. If they didn't, then some kind of sabotage it's talking about would destroy the binomial setting on that. So the independence of it on that. So it appears like it's independent on that one. Okay, so I'm going to go ahead and stop this video right here and then pick up with the second one, 8.1-2.